The learning objective for today's lesson is to be able to find the area under normal distribution curves. The probability distribution for a continuous variable is called a continuous probability distribution, and the most widely used continuous probability distribution is called the normal distribution. So over here we have the graph of the normal distribution curve. Let's look at the characteristics. So the graph of the curve is bell-shaped and symmetric with respect to the mean. The mean, median and mode are equal and located at the center. The curve is continuous, so you can see there's no points of discontinuity. And the curve approaches but never touches the x-axis. So you can see at the tail ends, it approaches but never touches the x-axis. And the total area under the curve is equal to 1 or 100%. Now let's consider a continuous probability distribution of times for a 400-meter run in a random sample of 100 athletes. So it might look like this. So over here we have the short time interval for some of the fast runners. Most of the runners, however, have a time interval of around here. And then you have some slower runners with a slightly longer time interval over here. Now, by increasing the sample size and decreasing class width, the distribution becomes more and more symmetrical. So let's increase the sample size to 1,000 athletes and decrease the class width. You can see it's become more symmetric than what we have over here. If we increase this further to say 10,000 athletes and decrease the class width, you can see it's becoming even more symmetrical. Now, if it were possible to sample the entire population of athletes, the distribution would approach the normal distribution as shown over here. For every normally distributed random variable, the shape and position of the normal distribution curve are dependent on the mean and standard deviation. Let's look at figure 1. What happens if we have a larger standard deviation? What's the effect on the curve? Well, you can see that a larger standard deviation results in a flatter curve. Let's look at figure 2. What happens when we change the mean? So let's increase the mean and keep the standard deviation the same. So you can see this results in a horizontal translation of the curve. The area under the normal distribution curve between two data values represents the percent of data values that fall within that interval. The empirical rule can be used to describe areas under the normal curve over intervals that are 1, 2 or 3 standard deviations from the mean. Now let's try to make sense of this using this diagram here. So in a normal distribution with mean mu and standard deviation sigma, we can see that the mean is located at the center. If we add one standard deviation to the mean and subtract one standard deviation from the mean, we get the following interval. And we can see that 68% of the data lies within one standard deviation of the mean. Likewise, if we add and subtract two standard deviations from the mean, we get the following interval, so that 95% of the data lies within 2 standard deviations of the mean. And again, if we add and subtract 3 standard deviations from the mean, we get the following interval, so that 99.7% of the data lies within 3 standard deviations of the mean. This is why sometimes, instead of the empirical rule, it's called the 68, 95, 99.7 rule. Okay, you can see the majority of the data lies within 3 standard deviations of the mean. However, the area under the curve should be equal to 100%, but this is 99.7%, so that leaves us with 0.3%. And using the symmetric property of the normal distribution, we can then split this 0.3% between these tail ends over here. Now when we add all these values up, we get 100%.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom, where we cover all UAE National Curricula American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. The first session is always free. So if you are interested in a free lesson, click the link in the description below. To book a lesson, you can always send us a direct message on Instagram at Mr. Mathematics. Okay, with that said, let's get back to our lesson.
Example 1. The heights of the 880 students at Al Sharq Secondary School are normally distributed with a mean of 168 centimetres and a standard deviation of 6 centimetres. So we'll make a note of this first. These are our two parameters. Part A. Approximately how many students are more than 180 centimetres tall? Now before we can do this, we need to work out some probabilities, and we'll use this graph of the normally distributed curve. We know that at the centre is where the mean is, 168. Okay, because the standard deviation is 6, what we'll do is we'll add on 6 to give us one standard deviation of the mean, add another 6, 2 standard deviations, add another 6, 3 standard deviations. And we can do the same on the left hand side by subtracting from the mean to give us the following. Now, 180 centimetres is what we're interested in, so we'll draw a line up from here. Okay, so we want to then find the corresponding area under the curve. So what area are we interested in? Are we interested in to the left or to the right? Well, we want more than 180 centimetres. So that'll be the area to the right of 180. Now you should recall 180, if you look at this, this is 2 standard deviations away from the mean. Now using the empirical rule, you should recall that 95% of the data lies within 2 standard deviations of the mean. So this area that I have in cream here is worth 95%. So that's 5% left over outside of that interval. Now because of the symmetric property of the normal distribution, 5% is then shared equally between these two tail ends. So half of 5% gives me 2.5%, and that's our probability. Now 2.5% of 880 is what we need to calculate, and that gives us 22. So about 22 students are more than 180 centimetres tall. Part B. What percent of the students are between 150 and 174 centimetres tall? So let's mark this off on our diagram here. So 174, 150, and we want to find the corresponding area under the curve. So that'll be between 150 and 174, which will be this area here. Okay, and now we'll use the empirical rule. Now if you recall from our early diagram, okay, 68% of the data lies within 1 standard deviation of the mean, so that's between 162 to 174. This next interval, okay, which is the next standard deviation to the left, this is worth 13.5%, and then our final interval over here is worth 2.35%. So we want the total probability corresponding to this area. So we add these values up to give us 83.85%. So therefore, about 84% of the students are between 150 and 174 centimetres tall. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now, while the empirical rule can be used to analyse a normal distribution, it's only useful when evaluating specific values, such as the mean plus 1 standard deviation. So if you look at this diagram, the empirical rule can only be used to evaluate specific values over here. It can't be used to evaluate values that are in between these specific values. Okay, and this is where the z values or the z values come into play. Now, a normally distributed variable can be transformed into a standard value or z value, which can be used to analyse any range of values in the normal distribution. So if we're given a specific data value, we can transform and find the corresponding z value by using this formula here. So if x is our data value, we subtract the mean mu and divide it by the standard deviation sigma. Now this transformation is known as standardizing, and the z value, which is also known as the z-score and even the z-test statistic, this represents the number of standard deviations that a given data value is from the mean. And we'll look at this in more detail later on in this video. Example 2. Part A, we want to find the corresponding z value if the data value x is equal to 24, the mean is equal to 29, and the standard deviation is equal to 4.2. So we can use this formula here. We substitute these values in, okay, to give us the following. We calculate this and we get approximately negative 1.19. And this has been rounded to 2 decimal places. And this is very common to do for z values. Now, this is our corresponding z value for the given data value x equals 24. Now remember, z values represent the number of standard deviations away from the mean. So this is a negative z value. So 24 lies 1.19 standard deviations below the mean. It's below because this is a negative z value. Part B, we want to find the corresponding data value x if we're given the z value 1.73, the mean 48 and the standard deviation 2.3. So we substitute these values into this formula and then that gives us the following. We can then solve for the data value x by multiplying both sides by 2.3 first. That gives us the following, and then finally we'll add 48 to both sides to solve for the data value x. Now this is our data value which corresponds to this given z value. Now if you recall, z values represent the number of standard deviations away from the mean, and this is a positive z value. Okay, so we can say this number here, which we've rounded to 52, 52 lies 1.73 standard deviations above the mean, and it's above because our z value here is positive. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following.